So motion programs are a special category of programs in Power PMAC that are intended for, as you can see by the subtitle, coordinating synchronized motion of axes. These are different from PLC programs, which you'll learn about later today, which are for asynchronous operations. This is specifically for grouping motors in a coordinate system and operating them at the same time. So any motors that you need to start and stop simultaneously will be all grouped into the same coordinate system and will be executed under the same motion program. So Alex covered coordinate systems, right? Yeah, okay, good. So a motion program has to run in a coordinate system, which means you have to have defined a coordinate system already before you execute a motion program. And Power PMAC can hold a great number of motion programs, basically as much as your flash memory and your RAM can permit, which is better than Turbo PMAC, which was limited to something like 224, so that's nice. You can run a motion program in several coordinate systems at the same time if you want, up to 128 separate instances of the coordinate systems. And if you're doing that, it's highly recommended to make use of the CS Global or Q variable types if you have variables within those motion programs that need to be common to several coordinate systems, but exist in separate instances. You can also call subprograms from within a motion program. Subprogram is a separate category of program which you will learn about later in the week that basically functions as a function does in other programming languages. So from your motion program, you can call the subprogram. Subprogram will operate top to bottom and then return to where you called it in the calling motion program. You can also perform general-purpose mathematical, logical, and I/O related operations in a motion program, in addition to synchronized motion. These, by nature, function asynchronously, but you can use a programming feature called synchronous variables to make these operations execute synchronously, that is, at the onset of a move. And motion programs also use the same flow control syntax as a PLC. Flow control comprises statements such as if, else, while, do while, and switch. Procedure for making the motion program comprises about 8 steps, the first of which is to define the coordinate system. We won't go into detail on that because you just learned about it yesterday, I believe. Next is to create the opening and closing brackets of the program. This is always the same. And between the brackets, you put the contents of the program. And then you select your move mode. In Power PMAC, we have 5 different move modes available, all of which provide a different way of sequencing your commanded trajectory. So the move modes are linear, circle, spline, rapid, and PVT. We will go into detail about each one in the next section. Next, you select absolute or incremental position programming mode. Absolute means any axis move you command is relative to the origin of the coordinate system. Incremental means that any move you command is relative to your current commanded position. Next, you want to select the speed at which to move the axes and the acceleration and time settings. So basically, how quickly do you want to get up to speed, and how long do you want the move to take. Next, you program the moves, download the motion program, and then execute the motion program. You can execute the motion program either online from the terminal window, a host PC application, or through a PLC or another motion program. So if you're executing the program from an online source, online meaning terminal window or a host PC communication program, you use this syntax, $MBNR, where the M is your coordinate system number wherein you want to run the motion program, and N is the name or number of the program. Programs can receive either a name or a number. I'll show you that in just a second. If you are calling the motion program from a PLC or motion program, you can use the start M:M command to start motion program N in coordinate system M. This is the basic outline of a motion program. At the top, we have the coordinate system definition. This is usually done prior to running the motion program and in a separate file. The only reason we have the coordinate system definition next to the motion program definition is for simplicity's sake and keeping it on one slide. Normally, you would put any coordinate system definition into the global includes folder in a file, for example, named coordinatesystems.pmh, and then you put your motion program in the motion programs folder in your IDE project. So step 2, create the opening bracket of the motion program. Here, the opening bracket is just open prog, and then after that you put the name or the number of your motion program. Next, you define your move mode. Here we're just selecting linear. Linear is what you'll use the most often because it's the simplest to understand. The next is to define the position programming mode. We define absolute position programming mode by issuing the ABS command. Then we define our speed, acceleration, and move time parameters. We want an acceleration time of 125 milliseconds. So we type TA125, an S-curve time of 35, which you indicate with TS35. And then we want to move for 1,000 milliseconds before deceleration, so we issue TM1000. And then our total move time will be TM plus TA, which is 1,125 milliseconds. And then lastly, we program the move. To begin the motion of multiple axes at the same time, you simply write multiple axes on the same line. In this example, we're moving X to 10 user units and Y to 20 user units by writing X10, Y20 on the same line. So they will simultaneously start and stop. If you issue them on subsequent lines, they will blend into one another and not necessarily begin at the same time. So be aware of that functionality in PowerPMac. And then to run this program, you would put it into your motion programs folder, right-click on your program, your project name, issue a download all programs, and then type #1j/ #2j/ to close the loops on motors 1 and 2, since those are the motors involved in the coordinate system. And then &1b1r to run program 1, which is how we defined it, in coordinate system 1, which is also how we define the coordinate system, from the terminal window. Note that in order to run a motion program, all motors in your coordinate system must be in closed loop mode before you can start it. An easy way to enable all the motors in your coordinate system is with the enable command. So you write the coordinate system number and then enable. You can also do &1a. Both of those will close the loop on all of your motors in that coordinate system. Okay, so your motion program can have a name or a number, like I said. So OpenProg1 or OpenProg main prog, these will both work. And wherever you want to reference the program, you can just use 1 or main prog. That includes using the start command or the call command, which you haven't learned about. You'll learn about that in the subprograms. But the call command allows you to call a motion program from somewhere else. And with the listprog command, listprog will dump the contents of your motion program to the terminal window or from wherever you called it, for example, a host program. And you would just write listprog main prog if you named it main prog, and that would work just fine. Okay, so I mentioned the 5 move modes, and we'll cover them a little bit more here briefly, and then each individual move mode in its own section in a little bit. The one you will use most of the time is linear mode. So this will interpolate your trajectory and actually blend subsequent moves together to create a smooth and continuous profile. It has a trapezoidal velocity versus time profile and will generally create a straight line path in Cartesian coordinates. So you go point A to B, it will just make a line between the two. Something to note is that it does produce a trapezoidal velocity versus time profile, so the acceleration is not necessarily as smooth as some of the other move modes that we offer, such as PVT or spline, but it is the easiest to program and the easiest to understand. Next is the PVT move mode. This allows you to specify an endpoint position, endpoint velocity, and amount of time to take from current position to the endpoint. This allows for the greatest control over your path because you're guaranteed always to pass directly through the programmed endpoint position. This is not the case for linear mode. Linear mode will always blend to the inside of programmed positions. PVT will use a Hermite spline path for parabolic velocity versus time profiles, which is a form of cubic spline and produces a very smooth velocity profile. Circle mode is for drawing arcs or circles and uses an algorithm very similar to linear mode. Subsequent circle modes will be blended together at the inside of points also. Spline mode uses a cubic B-spline and also produces a parabolic velocity versus time profile, much like PVT, but is programmed in a different manner. And the last mode is rapid. This is literally just a jog move, but with an axis name instead of a motor name, and also produces a trapezoidal velocity versus time profile. Position mode, absolute or incremental, are denoted by abs and inc, respectively. In your motion program, we talked about that already. And then to specify your move parameters, such as acceleration, velocity, and so forth, you use some different commands depending on what move mode you've selected. So in linear, you choose acceleration time with TA in milliseconds, and deceleration time with TD in milliseconds. Deceleration time is optional. If you don't specify it, PowerPMEC will assume you should use TA for the deceleration time as well. Choose S-curve time with TS in milliseconds, the move time before deceleration in TM, or the feed rate with the F command if you're using a feed rate axis. A feed rate axis can be selected by the frax command, and the units of the feed rate that you specify are in the user unit for your axis per chordx.feedTime. Chordx.feedTime is usually indicative of 1 second, but you can change it if you want to program your feed rates in other units, such as minutes or something. For spline mode, we select the amount of time spent in the different sections of the spline move, by writing spline and then the amount of time in each section after that in units of milliseconds. You can also specify different times in the different sections of the spline move. We won't get into great detail there yet because we'll talk about it later. Same thing for PVT moves. You can specify position, velocity, and time using a certain syntax to be discussed later. And then in rapid moves, you specify your accelerations and your speeds in the motorx.jog TA structure, motorx.jog TS structure, and motorx.jog speed structure, depending on the setting of rapid speed cell. So let me back up and explain that a bit. With a rapid move, you're not actually using the TA and TS command in your motion program to select the acceleration parameters. You use the parameters involved in jogging. So if motorx.jogTA is positive or greater than or equal to 0, you're specifying an acceleration time in milliseconds. If it's less than 0, then you're specifying acceleration rate in inverse units. So if you want to compute the rate of acceleration, you figure it out in units of counts per millisecond squared, then you invert it and add a negative sign, and then write that to jog TA. So if I want to accelerate at 10 counts per millisecond squared, I would invert this. You get milliseconds squared per count. And then you add a negative sign. And that's what you write to your jog TA. Same thing for jog TS. If you are using a positive value, it indicates the S-curve time in milliseconds. If it's negative, then it's an inverse jerk rate. It's a jerk limit. And then based on motorx.rapid speed cell, your rapid move will either use motorx.max speed in units of counts per millisecond or motorx.jog speed, depending on the setting. So 0 will be max speed and 1 is jog speed.
So in the motion program, do you need to specify these, or will it just use whatever the default for the motor?
You can do either.
Either.
Yeah.
So in the motion program, is it going to just set, say, motor 3, is it going to set these just for the move and go back to...
No.
So permanently, when you call that motion.
Yeah.
Okay.
So you could potentially, with a local variable, store the previous value, modify it for the program, and then reload it at the end. Yeah. That's a pretty common practice. Good question there. So here's a simple example of setting up a linear move. Just issue linear abs for linear mode absolute position programming. And then we select our acceleration settings with TATS and the time before acceleration with TM. So here's some diagrams explaining what I was just saying. So if you want to specify move time, TM is not the total move time. It's actually the move time from the onset of acceleration to the onset of deceleration. And then the total move time, as you can see, is TM plus TA. And the total acceleration time is not TA alone, but rather TA plus TS. We have more diagrams of that a little bit later, but if you are familiar at all with Turbo PMAC, this is a different convention from Turbo PMAC. In Turbo PMAC, the total acceleration was TA. So please note that if you are upgrading to Power PMAC. Now, if you modify TA, TS, TM, or F, the effects will remain active in the coordinate system thereafter until again modified. So if for example, you run one motion program, specify your motion parameters, program ends, you call a different motion program, and you don't specify the motion parameters, it will just use the previously used parameters. So keep that in mind. They actually get stored in some registers I'll show you later. So if you want to use feed rate command, you can issue the command with an F statement. So just write F and then the total speed you want your tooltip to move. And by tooltip, I mean your end effector represented by an XYZ point or something like that. for example. And you specify which axes to be involved in the feed rate command with the frax command. So by default, the Cartesian axes are involved in feed rate commands. Cartesian axes meaning x, y, and z. But you can add other axes if you want. For example, if you wanted x, y, and then a rotary axis a or something like that, then you just write it like that. And then a will be included in the feed rate command as well. So the units of feed rate are always your user distance unit over user time unit, which you set in chordx.feedTime. FeedTime is 1000 by default, which would mean that you're programming in user units per second. Right. Okay, and your total move time will actually be, like I said before, your TM, which is from the onset of acceleration to the onset of deceleration, plus the total acceleration time. The total acceleration time depends on whether you're using TA and TS, or just TA, or just TS. If you're using TA and TS, the total acceleration time is TA plus TS. If TA is less than TS, it's still TA plus TS. This slide needs to be updated, actually. It's correct later on, but not here. And your deceleration time will be TD plus TS. So to compute the total distance that your tooltip is moving, you can use the Pythagorean theorem. Total distance is the square root of the sum of squares of all axes involved in your move command. So if you're using x, y, and z, it's just the square root of x squared plus y squared plus z squared. And here are some examples of breaking up the total tooltip speed into componental speed. So if we command a move x3, y4, f10, means we want the tooltip to move at 10 user units per second, and a total distance of square root of the sum of squares, which is square root of 3 squared plus 4 squared, which is 5. And then the total move time will be the distance over the feed rate. So 5 user units over 10 user units per second is half a second. And then you divide the componental position by the time to get the componental speed. So we're moving a distance of 3 in x, divide that by the time, you get 6 units per second. Moving a distance of 4 in y, divide that by the time, you get 8 units per second. The other two examples are just a repeat of the same thing. Okay, so I mentioned before already, if you want to command several moves to execute synchronously, you put all the axes on the same line. But I didn't mention you can also programmatically compute the distance that you're commanding. So all the previous examples have written numeric literals to the axis move statement, like x10. But you can also encapsulate the axis move distance in parentheses and then compute it. So here we're writing y parenthesis sine of my global var, and then the result of the expression will be used as the distance you're commanding to y here. And the last step is just to download and run the program, like I've explained before. So let's talk about some other commands that are really useful for motion programs. If you want to create a delay, you can use the delay and the dwell commands. Each one functions a little differently. So, the basic idea is to write delay and then the amount you want to wait in milliseconds. But delay is weird in that if delay comes after a blended move, the deceleration time will be part of the delay. It will consume part of the delay. So if I write delay 1000, but I have a move before this with TD of 100, then it'll actually only delay 900. So you have to take that into account. And the nice thing about delay is that it will scale with changing time base. So if we're using time-based control, which is a special technique you'll learn about later, then the delay will scale as the feed rate changes in your coordinate system. So if for some reason your coordinate system drops down to 50%, then your delay will last twice as long in real life. You can also use programmatic delay amounts by encapsulating the command in parentheses. So we have delay parentheses my global var plus 45 here, and it will take the result of that expression and wait that amount of time based on the constraints I just described. If you don't want the wait period to scale with changing time base or to consider the deceleration time, you can use the dwell command. Dwell will wait the amount of milliseconds you specify in absolute real time, regardless of changing time base, and it does not consider the amount of time you decelerate into the command. So if you write dwell 1000, you will always dwell 1000 no matter what's going on. The downside is that you will lose synchronicity with the master signal if you're using time-based control, so consider that. So let's talk about some flow control. We have while loops in PowerPMech. Syntax is exactly like C programming, if you're familiar with that. We have the while statement, parentheses, a condition, and then curly braces to indicate what to execute while that condition is true. So pretty standard stuff. Note that in PowerPMech, to check equality in a condition, you use the double equal statement, just like C programming. That's different than TurboPMech, where you used a single equal. We have if and else, which function the same as in C. So if condition is true, execute the first clause's code, else execute the second clause's code. Some things to note: else is optional, you don't have to use it. And if your contents to execute for each clause occupy only a single statement, you can omit the curly braces. A statement is, for example, a variable in assignment or a function call or something. Note that a statement is different than a line. So if I had output 1 equals 0, output 1 equals 5, output 6 equals 8, those are 3 statements on one line. And you'd have to encapsulate them in curly braces because it's more than one statement. In PowerPMech, we also have the switch feature. So this is just like C. Switch will take a variable in parentheses and compare that variable to a number of discrete integer cases that you provide. In this example, we're seeing if the machine state variable, which is something you would have to have defined previously, we're seeing if that machine state variable is equal to 0. If it's equal to 0, we perform this action and then break out. If it's equal to 1, we instead perform this action and then break out. If it's not 0 or 1, we perform the default action and break out. Default action is indicated by default here. The break is optional. If you put the break, it will leave the switch statement upon reaching break. If you don't put break, it will continue on to the next case's statements before encountering a break or the end of the switch statement. So this did not exist in TurboPMech. Something else to be aware of is the jumpback rule. So PMech will not blend through multiple jumps back. By default, this is 2 jumps back, actually. But you can change the number of jumps back that will cause blending to stop with chordx.goback plus 1. So by default, go back is 1. The example on the left has a big while loop and an X move inside. And then before the X move is reached again, we see 2 curly braces. Each curly brace is a jump back. And since there are 2 there, PMEC will not blend through subsequent X moves here. It will do the X move, stop, do the X move, stop. The example on the right, we have an X move, single curly brace, an X move, single curly brace, and so on. So it will blend through subsequent X moves. That fixes the problem, or you could set chordx.goback to be larger to make the blending continuous throughout the program. All right, so PowerPMEC is constantly looking ahead to try to be efficient and pre-compute moves in advance. The number of moves it looks ahead varies depending on what is happening in your coordinate system. So here are some special rules. A lot of them won't make sense to you, so consider this more of a reference slide. But the first one should make sense. If you're using a rapid move, which is just a jog with an axis command, or if you have a dwell between moves, or if you've explicitly turned off blending with chordx.noblend equals 1, then PMEC will not look ahead at all. So it would actually cease pre-calculation of subsequent moves and anything else in the coordinates in the motion program until it passes that move. If you're using segmentation time and not using special look ahead, it'll look ahead 1 move. If you're using blending without acceleration control and no segmentation time, it will also look ahead 1 move. If you're not using segmentation time and you are using acceleration limits, it will look ahead 2 moves. If you're using special look ahead, it will look ahead as many moves as you specify. And if you're using cutter compensation, it will look ahead enough moves required to prevent interference between axes. The most important one to understand, however, is the first one. If your subsequent moves are stopping and you don't want them to, then this is the reason why. Right, so normally PMEC is looking ahead to try to be efficient, like I said, and pre-compute what it can. So if it sees, for example, X30 and then a bunch of non-motion commands right after that, it will just perform those non-motion commands as quickly as it can because it wants to be efficient, which means those non-motion commands may be executed at a time other than you desire. To illustrate, if I have in my program x1 and then output 1 equals 5, my global equals 10. PMEC will go, okay, I'll start executing this, and then I'll just set these at my leisure. That could be good or it could be bad depending on what you want. If you want to force these to be set exactly where you want in your motion program, you can use the synchronous assignment, which is a double equal. Now note that this double equal means something else in a condition, like in the while loop or the if, but in assignment, like here, it means execute this exactly at the onset of the next move. So if I put an x5 after these 2 synchronous assignments, both of these will be set exactly as x5 starts moving. So it will be in line with how you've written it in the motion program. That's all that example is saying. Something very important to note, however, if you want an assignment to occur exactly at the end of your program, you need to use a synchronous variable assignment and then a dwell 0. Otherwise, it may not execute at the point that you desire. So here, output 2 will be set equal to 0 exactly as the program ends. A dwell 0 technically counts as a sequenced move of 0 times 0 distance. So you can use that to force a synchronous variable to be assigned. This will work for the vast majority of variables in PMAC. It works for globals, CS globals, and PTR variables, except for self-assigned PTR variables. Self-assigned means that the definition points to an asterisk. So you had something like PTR, my PTR points to asterisk. You can't use synchronous assignments with this kind of thing. Don't ask me why. I don't know. Oh, and if you want to change the number of assignments allowed, you can modify chordex.syncops. By default, it's 8,192, which is most likely going to be enough for everybody. You can increase it if you really need. All right, so here's a simple move example. Very similar to what we were doing before. Linear absolute mode. You have a single axis in X, 1,000 counts per user unit. We only want to accelerate for 500 milliseconds, no S-curve. And we want a top speed feed rate of 5 units per second. So this first part is just configuring the motion parameters. And then we move to 10 user units, dwell for half a second with dwell 500, and then we move to 0 user units, absolute in X. And then to run the program, you first close the loop on motor 1, and then issue &1 B1R from the terminal window. And from a PLC program, you would do jog/1, start 1:1. If you plotted it, this is what it would look like, where the commanded position is in red and simply goes forward 10 user units and back to 0. Here's a slightly more complex move example. Here we are actually defining a loop counter, local CTR, and we want to iterate over the same move 3 times. So we start by setting CTR equal to 0, and we say while the counter is less than 3, perform this sequence of moves encapsulated in the curly braces. So just move X forward, hold half a second, move X backward, hold half a second, and then we can increment the loop counter with the ++ postfix operator. And then the move will execute 3 times. If you plotted it, you would see, indeed, the axis goes forward and back 3 times.